In 1945, I stood before an audience of physicists and divided everything that exists into two. Every particle of matter, every particle of force, every photon of light, every atom in your body, every force that holds the universe together. I put them all into two categories, and I had to name them. The first I named after my colleague, Enrico Fermi. He was famous, respected. Everyone in that room knew his work. The second, I named after a man that almost no one in that room had heard of. A man with no doctorate. A man whose paper on quantum statistics had been rejected by the only journal he sent it to. A man who had written 5 pages of mathematics in a city that most European physicists could not find on a map, and then mailed them to Albert Einstein because no one else would listen. I am not a man who gives names easily. I am not a man who gives praise. When I watched Heisenberg dancing with women on a ship, I asked him why he did it. He said, "When there are nice girls, it is a pleasure." I asked him how he knew beforehand that the girls were nice. I do not speak unless I have something exact to say. So when I tell you I gave this man's name to half the particles in the universe, understand what that means. His mathematics demanded it. His name was Satyendra Nath Bose, and no one believed him. The story begins with a mistake, or what appeared to be a mistake. In 1924, Bose was a reader in physics at the University of Dhaka, in what was then British India. He was teaching his students about the failure of classical physics, the problem of how hot objects emit light. Max Planck had found the correct formula in 1900, but no one had been able to derive it without mixing classical physics and quantum ideas together. Every derivation was a compromise, a patchwork of old and new ideas stitched together in a way that worked, but made no logical sense. Bose was explaining this problem to his class when he tried a different approach. He treated the particles of light, photons, as if they were fundamentally indistinguishable from one another. Not merely similar, identical. As if no photon had its own identity. As if you could not tell one from another. Ever. Under any circumstances. This seems like a small change. It was not. In classical statistics, if you flip 2 coins, there are 4 outcomes. Heads and heads, heads and tails, tails and heads, and tails and tails. But if the coins are truly indistinguishable, if there is no such thing as coin 1 and coin 2, then heads and tails and heads are the same outcome. There are only 3 possibilities, not 4. Bose applied this logic to photons, and out came Planck's formula. Perfectly, cleanly, without a single classical assumption. He had derived the most important equation in quantum physics using an entirely new way of counting. Bose did not fully understand what he had done. He knew the result was correct. He knew the method was new. But he did not grasp that he had discovered something that would divide all matter in the universe into 2 fundamental categories. He wrote it up in a 5-page paper, careful, precise, modest, and sent it to the Philosophical Magazine in London. And he waited. After 6 months, the journal rejected it. The referees did not see its significance. To them, it was a physicist from a colonial university making an elementary error in statistics. They did not realize the error was the discovery. Now here is where most stories would end. A rejected paper from a man no one knows, in a city far from the centers of European science. But Bose did something extraordinary. He wrote a letter to Albert Einstein, a man he had never met, the most famous physicist in the world, and he sent him the paper directly. I have ventured to send you the accompanying article for your perusal and opinion. Though a complete stranger to you, I do not feel any hesitation in making such a request, because we are all your pupils, though profiting only by your teachings through your writings. He posted it from Dhaka. It arrived in Berlin on the 4th of June, 1924. Einstein read the 5 pages, and he saw immediately what the referees in London had missed. Bose had not made an error. He had discovered that photons do not behave like classical objects. They do not have individual identities. They are, at the deepest level, indistinguishable. And this indistinguishability changes the mathematics of how they can be arranged, how they can be counted, and how they distribute themselves across energy states. Einstein wrote back to Bose on a postcard. He called the paper an important step forward. Then he did something remarkable. He translated the entire paper from English into German himself, the most famous physicist in the world, sitting at his desk, translating the work of a man he had never met, and sent it to Zeitschrift für Physik, the leading physics journal of the time. The paper was published in August 1924 under Bose's name alone. Einstein added only a short note. In my opinion, Bose's derivation of the Planck formula signifies an important advance. But Einstein had seen something that even Bose had not. If this new way of counting worked for photons, what would happen if you applied it to atoms? Einstein took Bose's idea and extended it. He applied the same statistics, the same principle of indistinguishability, to a gas made of atoms, not photons. And the mathematics produced a prediction that no one expected. At extremely low temperatures, temperatures close to absolute zero, the atoms would stop behaving as individuals. They would lose their separate identities. They would collapse into the same quantum state, all of them, as if the entire collection of atoms had become a single entity. Not a solid, not a liquid, not a gas. Something else entirely. A state of matter that had never been observed, never been imagined, never been named. Einstein called it a condensation. Today, it is called the Bose-Einstein condensate. Let me be precise about what this means. In every other state of matter, particles have individual identities. You can distinguish one atom from another by its position, its velocity, its energy. In a Bose-Einstein condensate, this distinction vanishes. The particles become one, not metaphorically, physically. They occupy the same quantum state, the same position in the mathematics, as if a billion atoms had merged into a single atom spread across the entire system. This was pure mathematics. No one had ever observed such a thing. No laboratory on Earth could reach temperatures cold enough to produce it. The prediction sat there in the equations, waiting for 70 years. Bose traveled to Europe after his paper was published. He visited Einstein in Berlin. He studied in Paris. And then something happened that I only learned about years later. Bose wrote a third paper, extending his statistical ideas. He showed it to Einstein. Einstein was not convinced. He did not support its publication. No manuscript of this paper survives. By all accounts, Bose was deeply disappointed. The sting of that rejection stayed with him for years. And then Bose stopped. He returned to Dhaka. He continued teaching, and he moved to other fields: chemistry, biology, literature, and music. But he never again produced work in quantum statistics at the level of that 5-page paper. Meanwhile, I was in Cambridge, building the theory that his work had made possible, and I could see what Bose could not, that his discovery was not a footnote, it was the foundation. Everything we were building rested on the principle he had found, that particles can be indistinguishable. Heisenberg, Schrödinger, Fermi, and I built the new quantum mechanics, and at the center of it sat two types of counting, two types of statistics, two fundamental categories of everything. One category followed the rules that Enrico Fermi discovered, and that I arrived at independently. These are particles that refuse to share a quantum state, that insist on their own space. Electrons, protons, neutrons are the particles that make up matter. I called them Fermions. The other category followed the rules that Bose had discovered. These particles lose themselves in the collective. They pile into the same state without limit. Photons and gluons are the carriers of every force in nature. And in 1945, I named them bosons, after Satyendranath Bose, the man who had gone silent. Let me explain what this means, because what Bose found is not a detail of physics. It is the most fundamental division in all of nature. Every particle that has ever existed, every particle in your body, in the air you breathe, in the light from distant stars, in the forces that hold your atoms together is either a boson or a fermion. There is no third category. There is no exception. This is not a classification of convenience. It is a law of nature. Fermions are the particles of matter. They are rigid. They demand exclusivity. Two electrons cannot be in the same state at the same time, and this is why solid matter exists. Why your hand does not pass through a table. Why atoms have structure. Why chemistry works. Why you are here. Bosons are the particles of force. They are generous. They share freely. They can all crowd into the same quantum state, and this is why light exists. Why forces can act at a distance. Why the universe is not just a collection of isolated particles sitting in the dark. Matter and force. Individuality and collectivity. Exclusion and inclusion. The universe is built from these two principles, and one of them carries the name of a man whose paper was rejected by the only journal he sent it to. For 70 years, the Bose-Einstein condensate remained a mathematical prediction, a theoretical curiosity, something that the equations demanded, but that no experiment could produce, because no laboratory could reach the temperatures required. We are talking about temperatures within a few billionths of a degree above absolute zero, colder than anything in the known universe, colder than the emptiest void between galaxies. In 1995, two physicists, Eric Cornell and Carl Wyman, finally did it. At a laboratory in Colorado, they cooled a gas of rubidium atoms to a temperature so low that the atoms stopped being atoms. They collapsed into a single quantum state. The Bose-Einstein condensate was real. They could see it. A single blob of matter where thousands of atoms had surrendered their individual identities and become one. The mathematics that Bose had written on 5 pages in Dhaka, mathematics that a journal in London had called wrong, was staring back at them from a laboratory in Boulder, Colorado, 71 years later. Cornell and Wyman, along with Wolfgang Ketterle at MIT, received the Nobel Prize for this work in 2001. They were not the first to receive a Nobel Prize for research that grew from Bose's ideas, and they would not be the last. By 2012, when the Higgs boson was confirmed at CERN, the count had risen to 7 Nobel Prizes, all tracing back to that 5-page paper. Bose received none of them. I must speak about this directly. Satyendra Nath Bose was nominated for the Nobel Prize. Oscar Klein, a respected physicist, was asked to evaluate his work. Klein decided it was not worthy of the prize. The nomination went no further. 7 Nobel Prizes. 7. All for work that descended directly from 5 pages written by a man in Dhaka in 1924. The Bose-Einstein condensate, superfluid helium, the Higgs boson, laser physics, all of it traces back to that paper. And the man who wrote it was told by the scientific establishment of Europe that his contribution was not enough. I did what I could. I gave his name to half the particles in the universe. That is not a small thing. Every photon that reaches your eye carries his name. Every gluon that holds an atom together. The particle that gives mass to all matter, the Higgs boson, carries his name. When physicists say the word boson, they are saying his name, whether they know it or not. But a name is not a Nobel Prize, and the absence of that prize is not a reflection of the quality of his work. It is a reflection of who was listened to and who was not, in the physics of the 20th century. I think about the moment he sent that letter. Dhaka, 1924. A man at a desk, writing to the most famous scientist in the world, knowing that the only journal he had sent his work to had told him he was wrong. And he begins, "Though a complete stranger to you, I do not feel any hesitation. No hesitation. That is the part that stays with me. Not the mathematics. The mathematics speaks for itself. But the act of a man who had been told by the entire establishment that his work was worthless, and who decided that one more letter was worth writing. What if he had not written it? What if he had accepted the rejection, filed the paper away, and gone back to teaching? The 5 pages would have disappeared. Einstein would never have extended the idea to atoms. The condensate would never have been predicted. The word boson would not exist. Half the particles in the universe would have no name. Everything that followed, the condensate, the superfluids, the lasers, the Higgs boson, the 7 Nobel Prizes, all of it depended on one letter from a man that no one in Europe had heard of. Bose saw something that everyone else missed. He saw that the particles of light have no identity. They are not individuals. They do not insist on being separate. And from this apparent error, this supposed mistake, he revealed a truth so deep that it splits the universe in two. I have known many brilliant physicists. I have worked alongside Heisenberg, Schrödinger, Bohr, Fermi, Oppenheimer. I shared the Nobel Prize with Schrödinger, but if you ask me whose single contribution deserved more recognition than it received, I would not hesitate. Satyendra Nath Bose died on February 4th, 1974, in Calcutta. He was 80 years old. He never received the Nobel Prize, but every time a physicist anywhere in the world says the word boson, they are saying his name, and that will outlast any prize ever given.